Boordism hypothesis, which says that you can learn something about this thing by computing certain homotopy fixed points of group actions. And that's what I'm going to talk about. But I'm going to start 2 category levels lower, actually, to make sure that people still follow the beginning. So let C be a category. And I want to talk about actions. So let's first start with C just being an object, then an action of a group of a G group. Oh no, the pen. On C is just a group homomorphism. So think, for example, C being a sets or vector spaces, and you recover the notion of an action. From G to the automorphisms of the object, and that's a group if you put it with composition. And what are the fixed points? So it's fixed points. So the set or the objects of all fixed points, they form a limit. And which limit? Well, it's some sort of limit over the diagram consisting of this group homomorphism. So you have a diagram of a part looks like this. It's a small part of a big diagram. And then you have the limit over this, and that's some other object that I call C fix. And you have some cone over it. It's a universal cone over this. And a single, in the case of sets, for example, this means that a single object of these, a single element of this consists of, satisfies an equation like this. If it, for example, in sets, so you recover a notion of fixed points of sets. And similarly, you have a notion of a quotient, and that's more of a colimit. So how do we do this 1 category level up? So where a group acts on a category. So if C is a category, so it's an object in the 2 category of categories, and I might as well put 2 group here, which I explain later what that means. And what's a group homomorphism? It's an E1 map of sets. So I'll change that to a E1 map of categories. So it's a monoidal functor to the automorphisms of the category, which form a monoidal category under composition. And then the fixed points turn out to be some sort of 2 limit. And well, you have to choose in between. These are all kinds of natural transformations connecting 2 group elements. So this here's a natural transformation, and here 2. And this causes a fixed point. So an object in this category right now is now an object in C, together with a specified isomorphism between, which tells me how the object is fixed. So the most relevant example for topological field theories is the case in which Z mod 2, which I call O1 for some reason, acts on vector spaces, which I take complex, finite dimensional, and I also restrict to the core. So that means that I remove all non-invertible morphisms. And I just have to tell you, okay, so what does the non-trivial group element do, which I call minus? It sends a vector space to its dual, and it sends a morphism to dual inverse, because I want to have something covariant. That's why I restrict it to the core. And then there's this other piece of data right here, which tells me how to combine 2 minuses with each other. And how do I combine 2 minuses with each other? So I have to give an isomorphism between the double dual and V, and there's a specific preferred one In case there's a finite dimensional vector space, it's the evaluation. So this is one example. Another example of a completely different flavor is if H is another group, then I can form the category which has one object and H as its morphisms. And it actually turns out to be the quotient of the trivial action, the group on the 1 point category. So this is the category with one object and morphisms H. And what is now an action of G on this category? Well, it consists of functors rho of G for every G. So that corresponds to group homomorphisms from H to H. And then we have the monoidal data of this rho. And these consist of natural transformations, which you can check correspond to group elements of H. And then there are several conditions. So the condition that corresponds to naturality gives you the following equation. So this is naturality of this, of the monoidal isomorphism, saying that this is a monoidal functor. So one equation. And then there's another equation, which is sort of cocycle condition. So like a twisted cocycle condition. And this in group theory is known as a non-abelian cocycle, non-abelian 2 cocycle. And from these, you can construct a short exact sequence of groups. So this is a sort of twisted semidirect product. It's not really a split semidirect product. And in fact, every exact sequence is of this form. And it turns out that the homotopy quotient, I say quotient, if I say homotopy quotient, I just mean quotient, of this is exactly this group. And there's also a converse statement in group theory that you can pick any short exact sequence and take a section, and through that you can actually construct an action. So it's a classification statement right there. And I'm going to tell you later about a generalization to one category level up. But first, I want to do a detour on topological field theories, which is, I think it's important because it's my main motivation, even though you don't really need it for the talk. And for that, I should recall some boring geometry things, but I'll just do the minimal amount that I need. So suppose I have a topological group and a d-dimensional real representation of it. Then I'm just going to black box that there exists in differential geometry, there exists a notion of G structures on manifolds that generalize things like orientation, Riemannian structure, spin structure, these kind of things. These are things that I have in mind. And then I'm going to just skip a million steps and tell you that there is from this, you can construct a symmetric monoidal category, which I call board d minus 1 G, in which objects are roughly manifolds with such G structures, and morphisms are boardisms between them, which are manifolds with boundaries. And then a topological field theory, so a topological field theory with this group in mind is a symmetric monoidal functor. And I forgot to tell you what is the symmetric monoidal structure on this. It's given by disjoint union of manifolds. So it's a symmetric monoidal functor, and it's usually denoted Z from this symmetric monoidal category to, well, any symmetric monoidal target, but here I want to take complex vector spaces together with tensor product. And sometimes I want to do Z2 graded, but for now I'll just do it like this. And let's look what happens in 1D. So in 1D, there are, well, at most 2 points, the positively oriented point and the negatively oriented point. And so these are zero-dimensional manifolds with orientations. And so this recipe tells me that if I have a TFT, then this is some vector space. And it turns out that you can show that the other point is the dual, and they are in duality via these half circles like this. So this is actually finite dimensional vector space. And if you have such a G, then there are more interesting Bordisms, it turns out. So for every G you can make the interval into a G manifold. So just schematically putting some G here. And it's not necessarily a Bordism between plus and plus, but it can be a Bordism between plus minus and plus. And this depends on this, depends on this representation that I chose right here. So we're in 1D, so GL1R is just R cross. So it depends on whether this is like a positive or negative number. And to make a reference to what we've been doing in the beginning, so this turns out to be a map, which I suggestively call FG. So that should remind you of the same fixed point notation I used before. From rho of plus minus of V, so this is this number, to V, and this is some isomorphism. And this action right here is the action that I introduced before on finite dimensional vector spaces. And this is not a coincidence. So in general, there's the cobordism hypothesis, which connects these pictures. So one-dimensional TFTs are, as a groupoid, equivalent to this thing, and we take G fixed points. Well, strictly speaking, we take pi 0 of G, where G acts through this pi. Okay, so this is a short, way too brief introduction to TFTs. If you didn't catch much of that, we're now going to go back to more abstract category stuff. So I want to get to one category level up. So I already used quite a couple of times the thing that you know, that a group is equivalent to a category, which I denoted like this, with one object and all inverses. Or I can equivalently see it, as I sort of indirectly already did, by saying it's a monoidal 0 category, a monoidal set G with all inverses. And what's the definition of a 2 group right now? 2 group, I just put everything, I put a higher category level everywhere. So it's either a 2 category with one object and all inverses, or it is a monoidal 1 category, just a category in all inverses, including inverses under tensor product, both under tensor and composition. So what's the main example with the above geometry in mind is, if you have a topological group, then its fundamental groupoid is a 2 group. And now we can go back all the way to the beginning, and I now want to go even one category level up. So now if I have a 2 category, I could now put 3 group, but I don't want to, but I can put 2 monoidal functor. And actually I should put tri-limits here, which makes me very uncomfortable, but there turns out to be a definition. People know something about tri-categories and tri-limits, please talk with me, I want to understand better, but this all turns out to still work. So from now on, I will just assume this setting and work together with Lukas Müller, I've been proving generalizations of the above. So for example, given two groups, so, which I now write curly, and an action on this thing, then there actually exists also a 2 group, which we call the semi-direct product, which satisfies the thing that I wrote down before. So actually, this is a correspondence. This. And there is a correspondence between these and exact sequences, whatever they are. So there's a notion of exact sequence that we define. And by choosing sections of these, you can get actions and you can get oops, I forgot the last term. This turns out to be very useful for computing fixed points that you need for TFTs. And the main examples that we want to look at, they all involve the 2 category, which I call S more of, which is the 2 category of superalgebras. So Z2 graded algebras over the complex numbers, in which objects are finite dimensional semi-simple algebras. 1 morphisms are, well, I want to, as before, actually restrict to, I want to, without saying what it means, I want to restrict to sort of finite dimensional kind of things and restrict to the core, and therefore I take invertible bimodules. And 2 morphisms are even invertible bimodule maps. And this turns out to have still a O2 action, as in the 1D case, it was O1. And its fixed points are, so there's still a cobordism hypothesis, which tells you that 2-dimensional TFTs, now they have to be extended. So they're actually functors between 2 categories, symmetric monoidal 2 categories, turns to be out to be equivalent to, if I take this as a target, to this category, FD twiddle, and then taking fixed points for this. And I'll just scroll down to go to the theorem because I don't have time to write it down. Let's see, where is it? So we show, together with work with Lukas Müller, I compute these kind of things for specific examples. So for example, for G equals spin, so spin structures, then homotopy fixed points, they consist of, well, bimodular isomorphisms like this, satisfying certain conditions. And our observation was that if this bimodule turns out to be a very specific thing, this condition is motivated by the spin statistics theorem, then actually this spin 2 fixed point is equivalent to a sort of Frobenius structure, which is symmetric. And then under the same assumption, we generalize this to more general groups. So any finite group, in a similar setting, you get a big theorem. And we generalize this even further to 2 groups, non-orientable case, and also so-called Hermitian or unitary topological field theory. Yeah, so I should say again with Lukas Müller. That's all I wanted to say. Thank you.
Okay, so can talk to, can thank the speaker. And there